Good evening, everyone, and hello there. My name is Eric Fleming, and this is my final presentation. A little fun fact before I get things started. The reason why I'm not in class with you guys is that I'm actually down the hall in another class taking a final right now. So I'm recording this video early because clearly I can't be doing two finals at once. The title of my project is, I guess, a misnomer, a coin counter. I'm just not counting coins. The goal of my project is actually to sum them all together. So the basic idea is, well, people are lazy, and if they have a lot of change, they might not want to add it all. So just take a picture with your phone, run it through this program, and it'll tell you how much money you have right there. When I started this course, I had a big question about whether I wanted to go into MATLAB or Python, and I figured, well, the professor seemed to lean towards MATLAB, so I did that. But when it came to some of the more general programming, my previous two classes were in Python, so I didn't know anything about it until then. But when it came to actually thinking about how I'd want to go about this process, Python has a lot of APIs that I was familiar with and helped me complete it. So let's talk about that process, right? Let me hide myself so that goes there. Actually, let's go to this slide. All right, so the process. So obviously, we need to take some images, and then we're going to segment the image of coins into polynomial time and non-polynomial time. Nope, really, we're going to segment them into pennies and not pennies. So I started off doing some color segmentations with HSV, and then I noticed for some really bright images, or sorry, not bright images, for really dark images, RGB, I was able to get a little bit more performance out of it. But from then, I would have two binary images, one with just the pennies and one with the nickels, dimes, and quarters. And there was, again, some useful MATLAB functions. One of them called, I think it was IMFindCircles, which was amazing. I had to tweak it a little bit, but it would give you the number of circular objects and then would also give you their radii, which is important because I used the radii to then distinguish between nickels, dimes, and quarters. So that's where the k-means algorithm comes in. I have all of these radii, and you had to figure out which categories they went into. So, I mean, sure, you could sort them, but because you can take the picture of coins at different distances, you can't just assume, oh, a nickel is always going to be 40 pixels. It's not, right? It depends on, it's always going to be a certain size. Let me see if I remember. It's going to be a radius of 10.6 something millimeters, but again, that's going to change in pixels with all those distances. So I'm using that algorithm to basically say the ratios will always be in constant proportion to each other no matter if their sizes change, and we'll classify them by that ratio. Okay, so some of the assumptions of my model which made it work. First, I took it against a black background. That's because coins are shiny, so pretty easy there. Although it can't be too shiny, so if it's highlighting, it's going to cause glare on the surface, and that's going to introduce a lot of artifacts, and so it's going to make it really hard. And you might even lose some of the coins, to be honest. To fix this, I also used high-res images. So when I took pictures of this with my phone, this was not the resolution that it spit out. It actually spit out images 4 times the size, and so I just cut each dimension by 2, and there you have it. If I were to take this project to the next level, I would try to I would try to segregate the coins if they were overlapping. So you'd have to find their centers, and then once you know what their centers are, you could find their radius from there. And then finally, the last assumption was that each image would have all 4 types of coins. Yes, I do know that there are actually more than 4 types of coins. We got the $half and the dollar coins. But this just ended up making the if-else logic a lot easier. It didn't really change how k-means worked because it would still be able to sort these into the various categories. Okay. So here is a preliminary result. So as you can see in this image, we have 9 coins, and we have our 2 segments. We have our pennies to the left and our not pennies to the right. So we got 6 and 3, as you can see, and here are the radii. So as you can see, the pennies radii are fairly consistent, and the not pennies radii are a little bit more diverse. But again, depending on the resolution of your camera, the reason why I broke this into 2 categories is what would happen if the dimes and the pennies were really, really, really close together. The k-means algorithm might not be able to differentiate them, and it might think that you actually have more or fewer types of coins than you do. And that's where having a high image resolution comes in and kind of saves it. I think when I was trying resolutions, I want to say 4 times smaller than what I'm currently using, it was really hard to distinguish the pennies and the dimes, at least based on size. So again, we're not going to go all the way deep down into how all that Python code worked of separating them, but I want you to imagine it was like a little bit of trial and error. So given an image, it would try to see if there were 1 type of coin, 2 types of coins, 3 or 4 types of coins. And then we have various metrics for measuring which clusters are the best. So in other words, is it a tight cluster or is it like a really nebulous cluster? And if there are 2 clusters, are they close together or are they far apart? So it turns out what you really want is you want tight clusters and you want them to be far apart. And that measurement is called the silhouette. So in the image that I just showed you, let's go back. As you can see, we have separated it into the pennies and the not pennies, but there should be 3 clusters here. So when I'm running this algorithm, I'm only running it on the not pennies, because once I know how many pennies there are, I don't really care what its radius is. I can just say, well, that's how many cents I have. So right here, the silhouette is the highest when you have 3 coins that you're clustering around. And it dips back down if you try to go to 4. So in other words, they might be tighter if you go to 4, but they're more spread out, so it's bad. Okay, so this is my overall process. So I did make like 5 or 6 functions along the way. So the first thing is I need to take my pennies image and my not pennies image. They're not really images, those are like the lists of the radii. Then as you can see, where's my cursor at? Okay. Then as you can see, I just take the length of the pennies, which is the same thing as their value. I then basically pre-process the data. It turns out the clustering algorithm doesn't work on 1-dimensional data. It works on 2, 3, 4, or higher dimensional data. So I just did like radius 1, 0, radius 2, 0. So I kind of faked it. So that's nice. I calculated the centers and the silhouettes and all that stuff. You choose the max silhouette. That's how you know you got the right one. And then I basically came up with a coin tray of my not pennies, right? So how many nickels do I have? How many dimes do I have? How many quarters do I have? That's that if-else logic I was talking about earlier. And then you just take a quick dot product of it. So once you know how many of each not penny you have, you just dot it with its value. Add it to the pennies that you counted before, and bingo, you got it. So I got to hide myself. But it does turn out that I think that that value is correct. That if you were to look at this, there is 83 cents here. So 50, 60, 83. And if I go further, here would be another result. This was the 8th picture I took, and this is $2.24. Okay, so some comments on segmentation. If I did this with just overall coins and then k-means, it was fairly simple. But again, the nature of it was that you needed to make sure that you had a high resolution, otherwise it would be hard to distinguish the pennies and the dimes. I also did need to fiddle with the parameters. So based off of the tilt of your camera, it might not recognize it as a circle. It might be too ovular. So to fix that, it was called a hue transform, and you would give it a coefficient. So I believe the default coefficient was 0.85, and I moved it up to 0.92, and that kind of got me all the circles I needed. As I mentioned earlier, pennies and dimes were harder to distinguish. Their sizes were close together. Too much reflected light made a penny fall into the same category as a dime. And some things I noticed when I was trying to segment the image was that, you know, the pennies, the red was always so much higher than the blue. So that was the easy way to screen it out. And then also, the green was always less than the red, but it was never like less than half of it. So I used those parameters to basically sort through greens and reds. And that is my presentation. So I hope you guys enjoyed it. I had a lot of fun programming on it, and if you're interested in looking at some of the Python code or the MATLAB code, it's on my GitHub. So thank you and have a good evening.